us get started. We are going to be doing today dot products. Dot products with 3D vectors. And so here we go. For any two vectors A and B, the dot product A dot B, that's how you say that out loud, is basically made up of this calculation. Multiply the x's, multiply the y components, multiply the z components, and add them all together. You can also get the dot product, right, that same number, by multiplying the magnitude of vector A by the magnitude of vector B and the cosine of angle theta. And if you can imagine this is 3D, these are the two vectors. The theta that we're talking about is the angle between the two vectors. And let's do some numerical ones. These are pretty much plug and chug. In question 2, the vector A is 4, 5, 0.2. Actually, it's a two-dimensional one, but who cares? It is now going to be that for me. I'm doing a three-dimensional vector of it. A 1, -2, and a 5. So if you wanted to find the dot product, I'm going to change that to a bit clearer. It would be 4 times 1 plus 5 times -2 plus 0.2 times 5. And that would be 4, take away 10, add 1, and that would be -5. So you can, and sometimes do, get dot products that are negative. Here's an example of one. You could get a dot product of 0, which is very interesting. And of course, you could get, as the third alternative, a dot product as a positive number. These three situations are directly related to the angle between the two vectors A and B. If the dot product is a positive number, as it is here, then the angle between the two vectors will be less than 90 degrees. If the dot product is a negative number, the angle between the two vectors will be more than 90 degrees. And if the dot product is 0, the angle between the two vectors will be 90 degrees. So if you were wanting to check are two vectors at right angles, by the way, we do use that word, but we like this word instead. So if two vectors were at right angles, right, and they could be at right angles that way, agreed, it doesn't need to be horizontal and whatever. Two vectors at right angles, we say that they are orthogonal. And if you wanted to do a quick check, are these two vectors orthogonal? You find the dot product, and if it's 0, you say yes, they are. And if it's some other number, you would say no, they are not. There is only one exception to this middle rule. Suppose A was a 0 vector. Wouldn't you also get a dot product of 0? Right, 0 times 1, 0 times 2. So when I'm talking about two vectors, dot product is 0 is proof that they're orthogonal. I'm making the assumption that neither of the vectors are the 0 vector, because all bets are off, right? And that seems reasonable. I think if one of them was a 0 vector, you'd pretty much know it, wouldn't you? You'd see it right away. So I don't want to make a meal of that. Isn't that pretty obvious how you calculate the dot product? So suppose you are being given some coordinates.
Can I see that page real quick?
Sure. Okay, suppose you are being told the coordinates of two vectors. Right. The first vector is going to be called PQ, and the second vector is obviously RS. And I want to find the dot product of PEQ, and the other vector is RES. So I need to get the components of that vector. Right, so if you want to do PEQ, right, isn't the formula was what, x2 take away x1, but I just go like this. Two take, right, second guy take away the first. Second guy take away the first. Second guy take away the first. It's as quick as that. Right, you want RS then. Second guy take away the first. Second guy take away the first. Second guy take away the first. Are you comfortable about that shortcut on finding the vectors joining PQ and QR, right? Second guy take away the first, and same for the other. Now the dot product is going to be 1 times 1 plus -3 times -3. Hinge on it. And finishing with 2 times 5. So I get 1, add 9, add 10, and I believe the dot product in this case would just be the number 20. So are we comfortable that if you were given a question where they didn't tell you the two vectors, but you gave the coordinates of the start and finish, that you could find the dot product in that case as well? Okay. Now, suppose you were given two vectors where they didn't contain numbers. Instead, they contained, in this case, variables P and Q. So and I asked you to find the dot product. Well, it would just be P times 4Q added to -Q times Q added to -9P, take away that guy. What would that get me? 4PQ take away Q squared. Oops, that's a negative as well. Take away 9PQ. So the answer would end up being -5PQ take away Q squared. So really, couldn't we do a dot product, even although the answer is not a number, we can still do the process of calculating a dot product. Are we cool on that? Do another one of these, a little bit different, just a little bit. So here's the two guys that we're going to get the dot product for. And it's going to be 2P times Q, 3Q times P, and that guy. And that's 2PQ, 3PQ, take away 5PQ, which ends up being 0. Oh, I do not even know what the numbers for vector A and B are, but their dot product is 0. What conclusion can I make about these two vectors A and B?
They form a 90-degree angle.
They do. Now, if you want to put in right angled, I'm okay with that. I think some of you might have even used the word can't say the word perpendicular. Right, aren't they just three names of the same essential storyline? So let me try and sell you why it's a good idea to get into the habit of calling these two guys orthogonal rather than right angled or perpendicular. In 2D, right angled, perpendicular work fine. In 3D, it still works fine. Would you agree right angles still look like right angled? What does it look like in 5D? Do you see the concept of being right angled disappears? Right. It doesn't have a meaning. So the word orthogonal replaces that, right? The word orthogonal is just the dot product is 0. Would you agree that you could do a dot product in 5 dimensions, right? And couldn't that answer be 0? But physically, that wouldn't mean the two vectors were at right angles, because right angles is really a measure in what, the 2D world. It doesn't really transfer. So if you're wondering why I push orthogonal, it's a more precise definition once you leave 3D. So you might as well just get used to it, right? Okay. So let's move on to calculating dot products using this formula. So a nice easy one would be, an example of that would be question 7, where you're told the magnitude of A is 8. You're told that B is 4 and that the angle between them is 30 degrees. And so we want, unless they tell you to 2 decimal places, we want exact values for these types of questions. So it's going to be 8 times 4 times the cosine of 30 degrees. And I've got a little guy over here. There we go, our unit circle. If you find 30 degrees, you get this coordinate here, what I'm pointing at. All you need to do is remember, is the cosine the x coordinate of this unit circle, or is the cosine of 30 degrees the y coordinate of this guy?
X coordinate.
Yeah. So what you have is 8 times 4 times root 3 upon 2. That partially cancels. And I believe the answer is 16 root 3. Would you agree it's just a plug and chug, right? Plug in the 8 for A, plug in the 4 for B, and find the exact value of the sine or cosine. And you might want to find a unit circle, at least for the exact answers. Now, if that was 22 degrees, wouldn't you just do the whole thing in the calculator and say 15.123, because the answer would have to be a decimal. But if that's a standard angle, 45, 90, pi upon 4, you should be able to do it as an exact value. Are we good? Do you need another one like that, or can I skip this kind of question? Is one enough, or do you want to see another one? We're good.
One's
okay.
enough.
One's enough. And let's move on and show you a real sneaky question. I want you to imagine that that is an equilateral triangle. And the reason I know it's equilateral is because all 3 sides are the same. And we have got some vectors on this picture. Going in this direction is called the vector W. Going down this way is going to be the vector V. And going down this way is the vector U. So this is all in the picture. I'm just copying it here. And we are going to be asked two dot products. One of them is straightforward and obvious, and the other one is not what you expect it to be. Now let's do the obvious one first. It's the magnitude of u times the magnitude of v times the cosine of the angle between them. Oh, and by the way, these are all unit vectors. So when you are told something is a unit vector, you're being told that its length is 1. So in this question, it's going to be 1 times the cosine of the angle between the two vectors. Now, this one here is u, and this one here is v. So in this case, the angle between those two vectors is that angle there. How many degrees or radians, it doesn't matter which, you're going to get the same answer at the end. How many degrees or radians is that angle?
60.
60, okay. Or pi upon 3 if you're that way inclined. Now, if you find 60 degrees and you get its x coordinate, you get that it's 1 times a half, and the answer is a half. That one I'm calling the straightforward one, right? Not much happening. And I promised you this one's not what you'd expect. Well, of course, it's going to start off as the standard formula. Now, if you look at the v, he's going this way. And if you look at the u, he's going this way. So it's 1 times the cosine of the angle in between. And the cosine is not 60 degrees. The angle between the vector u and w is not 60 degrees. Now, you're looking at that corner there and you're saying, but that is 60 degrees, because so is that one, right? And I agree, where my finger is pointing, this angle in here is in fact 60 degrees. No arguing with that. But I'm saying that the angle between the vectors u and w is not 60 degrees, because it isn't. What is that angle?
Is it 120?
Correct. Why?
Because it's the outside angle.
Right. If you imagine this vector u and I slide it down the way, wouldn't it be here? And when you're talking about the angle between two vectors, you don't care where the vectors are drawn, because vectors could be shifted, right? You can move them around as much as you like. The angle between two vectors is, pick a point that they both share. Isn't the angle that guy? Does that make sense? That the angle between u and w is in fact 120 degrees. I'm not liking some of the faces I'm seeing. Does that make sense? Right. So when you are measuring the angle between two vectors, you measure the angle at a certain point, and then both vectors have to leave that point. And so the angle between them is this angle here. This vector is coming down the way, and this one's going the cross way. This vector here actually starts up there, doesn't it? And travels that way. See, that doesn't work. So I just picked it and I slid it down. And that ends up being 1 times negative a half. And so the answer here is negative a half. I wish they had more versions of this type of question, but I guess they're kind of hard to create. So that's the only one we've got. It's a very special one-off question. Okay, I'm about to move on to finding the size of an angle between two vectors, right? To find out how big that angle there is. And what we do, let's write this down first, how to find the angle, call it theta, between any two vectors. Well, we take this formula and we take this formula and we put them together. And if you make this guy equal to this guy, you get the relationship that A1B1 plus A2B2 plus A3B3, this guy, is equal to the magnitude of A times the magnitude of B times the cosine of the angle in between them. And then if you divide both sides, you get that the cosine is A1B1 plus A2B2 plus A3B3 divided by the magnitude of A times the magnitude of B. And it's very often written, because it's a little bit easier to write it like that. So the formula for the cosine of the angle between two vectors is the dot product, and by that I mean this calculation, divided by the magnitude of A and the magnitude of B. So let's try that. Suppose I have a vector A and its components are 1, 2, 2, and I have a vector B and its components are 3, -4, 12. And I want to find the angle between these two vectors. So you can imagine this pen might be one of them and that pen there is the other. And if I rotate it, you can see it's about 100 and something degrees. We're trying to find this angle. So we need to know some things. We need to know a dot product. We need to know two magnitudes, and then we can put them together. So let's do the magnitude of A. It's the square of the components. Square root of 9 is 3. Magnitude of B. Square of the components. And it ends up being 13. You need to know the dot product. Well, the dot product is going to be 1 times 3 plus 2 times -4 plus 2 times 12. And that's 6, take away 8, add 24. And I believe that is 22. I'll pause for a minute. Has anybody seen it? I'm not saying there is one, but has anybody seen any numerical mistake? Because I can see one now.
Wouldn't it be 3 instead of 6 at the beginning?
Yeah, and so that's going to make this answer a little bit smaller, isn't it? It's going to make it, I believe, 19. Are we good now? Okay. So you put the package together and you're going to get that the cosine of the angle between them, theta, is the dot product, 19, divided by the magnitude of both of them. And in this case, it's going to be, well, let's just take it one step further. It's going to be that fraction. Great. Don't overthink this. How do you find the missing angle if you know what the cosine is?
Take the
What calculus? Yeah.
The
Second.
inverse cosine.
Yes. Don't overthink it. And we'll assume that it's to be degrees, because I know it is. And it tells us it is. I'll go into mod, and guess what? I was in radians, so it's worth checking. I mean, that's an easy mistake, but it could happen. So we're in degrees, and we're going to do the inverse cosine of 19 divided by 39. And the answer, let's say to 1 decimal place, is 60.9 degrees. In WebAssign, when they ask for the exact value, they mean this guy. And if they ask for the approximate value, you get that guy. I believe that when you type in the answer in WebAssign, yeah, let's show you how you type in inverse cosine of say 1939, just for an example. So you click on there. If you go down to trig, do you see they have an inverse cosine button that you can hit? And then you can type in, I'm assuming you're looking at WebAssign, agreed? Okay, so you hit the inverse cosine. So it's under trig, inverse cosine button. And then you can put in the fraction 1939. So I'll go to operators, put in 1939. Now, there may be other ways, there's probably too many brackets. There may be other ways to type that in, but that one I know works. Right, you might be able to cosine to the power of -1. I'm a little bit frightened of that because that could be a -1 power, right? And that's not what we mean when we do that. So I would play safe and just do that. And the approximate answer in this case would be 60.9. These are not the numbers I was using, but this is what you would do if they were. Are we cool on that?
Mr. Robertson, I have a question.
Yes.
So why, when you rounded it to the first decimal, did you get 60.9 instead of 60.8?
I was just making sure that people were paying attention by deliberately making a mistake.
Okay.
Do you believe that? Not one person in this class should believe that. But it's really cool because what that means is that you know what's going on, right? And I always like that because it means my students are doing the thinking for me. Would you agree as a process goes, it's a little bit number crunching, but it's not that difficult. Would you agree you can get a dot product, you can find two magnitudes, you stick the package together and you get an exact value or an approximate value. And if they wanted radians, well, that would still be the exact value, wouldn't it? And this would be some different decimal because in radians, 60.8 degrees is not the same thing in radians. It's about 1 point something in radians, 1.2, I think. Do you want to see another one of those? I think so. So I'm going to give you two more vectors and I'm going to change the way they're written. There's my first vector A. There's my second vector B. And it's the same question, find the angle between these two vectors. I immediately turn them into that because it just makes my life so much easier. Right. The magnitude of A then is 3 squared plus nothing squared plus 2 squared, right? That's the square of the components. 9 and 4 gets me 13. The magnitude of B is 4 squared, -1 squared, and a 1 squared, and that gets me 1, 2, that gives me the square root of 18. And the dot product, well, that's going to be, well, do it here, 3 times 4, plus 0 times -1, plus 2 times 1, and I believe that is 14. So the cosine of theta is the dot product divided by the magnitude of these two vectors. And so in this case, it's going to be 14 over the square root of 8, square root of, well, okay, square root of 13 and the square root of 18. I wouldn't spend any time making that look pretty. Just leave it like that. So you want an exact value. It's the inverse cosine. And if you want to know it in degrees, oops, click over here. Oh, by the way, this question here is a version of question 12. So inverse cosine, 14 on the top divided by square root of 13 times square root of 18. And let's see what weird thing might happen. Oh, error. What happened there? Okay, that's what I typed in. 14 looks good. Square root of 13, square root of 18. None wrong with that. Yet it's wrong.
Maybe if you put parentheses around the two square roots, it will like, oh, I see. So you put a parentheses at the end of it, but you didn't put it at the beginning of the square root points, if that makes sense. So you have no parentheses, square root of 13 times like the square root of 18 parentheses, and then like you have another ending one, but you just didn't begin with the parentheses.
Ah, so let's see. So I'll put in the square root of 13 times, how did I do that? Square root of 13, there we go, times square root of 18, there. Now, on your calculator, that's what needed to be done. If you don't have this set of brackets, error. And you might say, what the heck is going on there? Order of calculations is what's going on there. The calculator thinks I want to do that. That's fine. Then it thinks I want to do that. Because that's how it's going to interpret the calculation. It interprets it. If there are no brackets, it does it from left to right. Can you see that that's going to generate an answer bigger than 1 and you can't get inverse cosines? So I guess the moral of that story is sometimes you have to be careful about brackets. And 23.8 is the answer to 1 decimal place. So we're cool with that. So let's add some problems to it. I'm going to give you a triangle in 3D space. And I'm making no attempt to draw this accurately, it's just a placeholder. P, Q, and R. And we want to know this angle here. So the question is, find the angle RPQ, right? Find the angle RPQ. And we're going to be using these guys, right? Where should I start? By the way, this is similar to question 13. I mean, I've got some coordinates, but that's not what I can use.
Vectors of PQ and PR, and then solve for the angle between them.
Sounds good to me. And would you agree that the angle between these vectors is going that way? What would be wrong if I found the PR and the QP? What would be wrong with doing it with this combination rather than this one? There's PQ. QP is going that way. If you start at the same point, wouldn't I actually be getting the complement angle? So if you're going to find the angle at P, make sure both of them start with a P, right? It is important. PQ is not the same thing as QP, right? The orientation is different. So one take away that guy take away that guy take away that guy. PR. Two take away that guy, five take away that guy, one take away that guy. The magnitude is 0 add 16 add 81, which is the square root of, I hope, 97. Magnitude of this vector is 1 plus 9 plus 9, which is equal to the square root of 19. The dot product of these two vectors is 0 times 1 plus negative 4 times 3 plus negative 9 times negative 3. And that's negative 12, but that's plus 27. So I believe the answer is plus 15. Okay, I'll pause for a minute. Do those numbers look good? That one, and that one. As far as you can tell, are we good? I can't see any mistakes, but it doesn't mean there isn't one. Call it good then, move on. So if you want to find the cosine of the angle between these two vectors, it's the dot product divided by the two magnitudes. It's going to be 15 divided by those two guys. So theta is going to be the inverse cosine of that ugly calculation. And I will go over here, do an inverse cosine. 15 goes on the top, divided by, put a bracket in, so I don't have the same issue I had last time. 97 times square root of 19. And the answer is about 69.5 degrees. So can we now find all three angles of a triangle in 3D space? For instance, if I then moved on to the angle at R, right, this one up here, wouldn't I find RP and RQ, right? Remember, if you want R, make sure you start at R's, right? So the angle here would be an RP and an RQ. And then I'd do all this. And I'm going to pretend I know the answer, which I don't. But let's suppose that this one ends up being 16.5, just for argument's sake. Couldn't I then move on and find the third and final angle? And I could do this process, couldn't I? I could do QR and QP and do all the stuff. Or I would save a lot of work if I did what else?
Just know that 180 is the max, so you
Right,
can just
and-
subtract.
Yeah. So take the two you know and what you got. And the question I'm talking about, that's exactly what you're being asked to do, find all three angles. So you get that one doing it this way. You have to find this one doing it this way, but the last one you get for free, right? So add up what's there and see what's left from 180. And we are done. I think today's going pretty good. You agree? I think the only one I had issues with was that equilateral triangle one and trying to convince you that the angle was 120 and not 60. That's maybe the only one I was picking up vibes. Apart from that, seems to be going good. Right. Let me zoom over to show you the next question, which is 14. We're going to use two terms that we have met before, one of which we kind of know and the other we don't know how to prove yet. If you're given these two vectors, if they are orthogonal, how would you know that?
Dot
If
product
the
equals
dot
zero.
product was
Right.
0.
So can you do a dot product, and if it's 0, it's orthogonal? Right. Let's suppose you did the dot product and it was 17 or something. Well, okay, so it's not orthogonal. But there are two choices. The one we haven't really dealt with, the parallel one, because if it's not those two, you pick neither, right? So how do you tell if something's parallel? Well, if you take the two guys, there are two ways to tell if two vectors are parallel. The one is using the dot product and the angle between the two vectors. What angle would you get if two vectors were in fact parallel?
180.
Yeah, or
360.
that's correct. Oh no, 180 or 0. And that works. So you could use the dot product. You know the answer that we got earlier? You could use the dot product, but then move on and find the angle, right? And if you get the angle and it's 0 or 180, you'll get it 0 if the cosine of theta was equal to 1, and you'd get 180 if the cosine of theta was -1, right? That's one way to do it. There is another way to tell if two vectors are parallel. If one vector is parallel to a second vector, let me do it down on the thing, that way I can show you, because it's kind of visual what I'm trying to say. I want you to imagine my two pens, right? Well, let's make one of them longer than the other, right? Vectors can be parallel. They don't need to be the same length, agreed? They just need to point in the same direction. If vectors are parallel, won't one of them be a multiple of the other? So if you look at the first vector, let's pick a vector like 15, -12, and 9. And the second vector, so that one's called U, right? And the second vector called V happen to be the numbers -10, 8, and -6. If you wanted to check, is this vector a multiple of the other, especially when the numbers aren't obvious, like, oh, that one's twice this one, divide the corresponding components. Have you noticed that each one of them is -1.5? Isn't one of them 1.5 times the other? Technically, U is 1.5 times V. If you can get the same ratio, they're parallel. So just look at the X's and divide, look at the Y's and divide, look at the Z's and divide. If the answer's the same, they're parallel. And that's a little bit less work, isn't it, than trying to find, you know, the length of the vectors and doing all the other stuff that you would have to do. So you can use dot products to find out if something's parallel. The angle will be 0 or 180. And because parallel doesn't care if you point, you know, this way and that way, you're still parallel, right? And so 0 or 180. Or you can do divide, 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 divide. If it's the same answer, they're parallel. And if it doesn't fit the first two, then it's the next two. So that's what 14 is like. 15 is the same. Oh, this one is connected to the question that we did with the 3 points of a triangle. This is question 16. And we are being asked, is this triangle right angled? So you imagine this is P, this is Q, and this is R. Pay no attention to the shape, it's just the way the triangle appeared. How could you prove or disprove that this triangle is right angled?
Find the angle of Q.
Say again?
Find the angles, or two of the angles.
Aha. So couldn't you find this angle, this angle? I guess you could find all three. If any of them are 90, wouldn't that be right angled then? Okay, so it was a bit like that big long question. Since we're only interested in it being right angled, if I wanted to save myself a little bit of work, couldn't I just stop at the dot product of each of the combinations? And if any of the three dot products, because it only happened to one of them, right? If any of the three are 0, haven't I got my proof? So you can actually find all three angles, just do it the long way, and one of them will be 90, in which case it's right angled, or none of them are 90, in which case it's not. Or a slightly less work version is just find, for instance, PQ and QP, and just do the dot product. And if that was 0, hey, it's right angled. And if it's not, couldn't you then do PQ and PR and then QP and QR? And if none of them are 0, then it's not right angled. If one of them 0, stop looking, right? It's right angled. 17 is the same as 16. And I think that's a natural place for us to finish. So say your last name and bye-bye for now. I'll hang about for any questions.
Professor,
Yes.
can you explain the right angle thing just a tiny bit more to me? Because I think I'm getting it, but not 100%.
Sure. Are we talking about prove that this is a right angle triangle or not? That kind of question?
Yeah.
Right. So what you can do is you can find all three angles. So the first method was you find the angles PQ and R. For instance, if I wanted to find this angle here, right, this angle here, the one that's called Q, what I would do is I'd find QP and QR. I would then go through the whole process of finding the angle, and that would be the cosine of theta is QP dot product QR divided by the magnitude of QP times the magnitude of QR. And eventually I would be able to find out what theta is. And let's just pretend that I did that and it was 32 degrees. Well, I would then find the angle here. So the angle at Q was 32 degrees. To get the angle at P, I would just do PQ and PR. And let's say I did that one and, oh, my learning system's rubbish here. The angle at Q then was 32 degrees. Then I did the same process and I got the angle at P and it was 70 degrees. What would the angle at R be if that was the real numbers that we got? So we know these two. What would the third one have to be without bothering to calculate it? Right, add them up, see what's left. So 102, 78 degrees. So this would be, nope, it's not right angled. Imagine I went through the same process and I found angle Q and it was 90 degrees. When I stop there and say, yes, it is right angled, because if that's right angled, the thing's going to work. And that was the first way that we set this up. And then the second way is we did a kind of shortened version. Let's suppose I'm interested in the angle here. And I'm just checking, is that right angle? That's all I'm checking. then I would find the dot product PQ and PR. And if that answer was 0, then that means that the angle is 90 degrees, in which case we would say yes. If I found this dot product and the answer was some other number, let's say 5, then it's not right angled. So I'd say, okay, you're not right angled, but then I'd move on and I'd check, maybe that one is right angled. So to check this one, I would do QP and QR. And I'd find the dot product. And if that one was 0, we'd have 90. And if that one wasn't, we wouldn't. And then you'd go and you do the last one, which would be RQ, and compare it to RP. And if you took those two guys going there, the dot product, if that was 0, yep, you'd have for 90. And if that wasn't 0, then you would be saying no. So each angle gets tested. If it's not 90 degrees, you move on to the next one. If it's not 90 degrees, you move on to the last one. If none of them end up being 90 degrees, it's not right angled. You don't actually need to, in the second method, find the size of the angle. You only need to find out if it's 90 or not. And for a dot product, 90 means 0 and not means it's not 0. So if the dot product is 0, bingo. If it's not, you move on. Dot product, if it's 0, yep, it's right angled and the right angle will be at Q. If it's not 0, move on. If the last one was 0, you think, darn it, I wish I'd got it the first time. It means that the angle is right angled. And if it's not 0, it means the third one is not right angled, not 90 degrees, same thing. And that's kind of the process. So it's a kind of process, check an angle, check the last angle. In this one, you only do the dot product part. Here you do the whole thing. You find the size of the angles. This is a little bit less work because you don't need to find an exact number for every angle that's not 90. You just need to find out, is it 90 or not? Does that help?
That helps perfectly. Thank you so much.